Good morning, everybody. So, I am François Chabot. I am the lead programmer at OPAL-RT since about a year and a half now. And this is my colleague, Philippe Beauchamp.
Hi, everyone.
So in today's presentation, we're gonna go over basically the next iteration of RT Lab. RT LAB11 represents a big change for our product line, and there's a lot of new features. We've got a lot of ground to cover. We're also gonna have a live demo of our in-progress build. There's a lot of details that are still up in the air, but functionality-wise, what you're going to see is what we're planning on delivering. So without any further wait, what is RT LAB11? Well, RT LAB11 is basically a completely different paradigm around the simulation building workflow compared to RT LAB10. Basically, there's two things we're bringing to the table. The bigger thing is faster iteration. We are really crunching down on the amount of downtime, on the amount of wait you have to do as you are working on a given simulation. Also, and this is was a bit of a surprise for us as well, we are actually going to be getting better performance out of our simulations as a side effect, which is very good. So, at the top level, what we've been doing is that we had two other products. For those of you who are familiar, we have Test Drive and Orchestra, which are two completely separate products from RT Lab that have been providing a lot of cool features to our customers. So what we've done is take the fundamental ideas behind Test Drive and Orchestra and actually integrated them within the main RT Lab experience and actually getting all those features really within the actual underlying fundamental system. Also, and this is actually a very important thing to mention, we are bringing in a new paradigm, a new way of building simulation. That does not mean we're throwing everything out the window. If you had models that worked in RT Lab 10, they will still work in RT Lab 11. There's a few things that are not going to be compatible, so if you had IOs in RT Lab 10, you're not going to be able to mix and match that with RT Lab 11 IOs, but existing models will still continue to function. This was something that we really cared about. We didn't want anybody to have to throw anything they've built out the window. So,
we have an example here to try to explain and illustrate the different change that we have made to RT Lab. So let's start with a very simple example. Let's say that we have a race car here, and we have on this race car a semi-active suspension system that we want to control. So in this case, that's an example in mechanical control where we use the real-time simulator as a controller. So we have this actuator, so it can be any type of actuator. In this case, it's an actuator that we can change the current that flows into a coil and that change the viscosity of the fluid inside the damper of the car so that we can adjust in real time the damping of the race car. So you have a car that is on the track, you have a real-time controller that can be an embedded PC that will run real-time closed-loop control algorithm that will adjust the suspension while the car is on the track. So that was something real from the École Polytechnique of Montreal Formula ACE project. So we have, so in order to control the damper, we have sensors, and those sensors, for example, it's a simple linear variable resistor. So we measure the position of the wheel. So the idea when we use RT Lab is to have a bunch of sensors. For example, we have inertial sensors, we have position sensors that will convert some mechanical movement to voltage. And then we can feed those measurements to the real-time controller. So in this case, we show an OP4500 box that will run the real-time algorithms. And then we take the output of the control algorithm and send this to the actuator so that we can actually close the loop. So that's the typical way of using the real-time simulator for control. It can be the opposite also. We can say, okay, let's have a virtual car and let's use the real controller so we can do both. So in this case, we just show for control. So we have in the middle here, for example, we take a PID control that will read the position in centimeter and send the control command to a chuck to adjust the damping of the car. So let's look at what we used to put in the model to make this work using the previous version of RT Lab, and then this will bring us to the new modification or the new feature that we're adding to RT Lab. So I will let François explain this part.
So the first thing is, given the actual model, so originally somebody built that Simulink model with a PID, with an input and an output of the expected data flows. To that model, we'll be adding OP5142 blocks to basically import inside of the model the S functions that will actually provide the data coming from the hardware and send the data back to the hardware. But really, that's not enough. Oh, we're going to have the inputs, my apologies, and the outputs, of course. But that's not enough at the end of the day, because more likely than not, we'll want to be calibrating the values. So we'll be modifying the Simulink model to add calibration mechanisms. In that case, a gain and an offset both on the input and the output. We're going to be getting the raw input in volts, which is then we're going to be converting into engineering dimensions, in that specific case centimeters, and we're going to have a mechanism to actually calibrate the offset of that data. We'll be doing the equivalent on the outside as well. But even then, that's not enough to have an actual functioning simulator. We need to add more stuff to this. So in that specific case, this is what the actual end model will look like in Simulink once everything is said and done. We have our drivers that are being used for IOs. We have our calibrations that are there. Of course, the calibration, we want it to be persistent. We don't want to have to calibrate from scratch from every simulation. So we'll be adding persistence to the calibration through our up parameter manager, which is one of our blocks in our block library that allows for that feature. Also, having a simulator like this is not really useful without being able to introspect it. So we're going to add a GUI to it. So we're going to add scopes and various types of visualization mechanisms. And now, because we have parts of this that runs in real time and parts of them that will run on the host, we have to break it down into two subsystems, because some of it is going to run on the target, some of it is going to run on the host. So we're ending up with this big system, which, by the way, is absolutely okay. There's nothing wrong fundamentally with this. This is how RT LAB10 works, and this is definitely the best way to work within that context, because every single piece of this will get compiled within the simulator, and then we'll have very tight integration with the generated code with RTW, which is which at the end of the day is what gave RT Lab its performance, which is the main selling feature right now. So, but at the end of the day, this is what we wanted to build. That little thing there at the top, that is the model we're interested in. And that's the idea behind RT LAB11. We're making every effort to make it so that the model, the actual MDL file that the engineer builds, is actually as close to just the model of the thing they're trying to simulate. So, in order to do this, we basically set ourselves down with a few important principles. First, contextual independence of simulation elements. The model needs to be built in a way that it doesn't know what it's connected to. It might be connected to an HIL simulation through the I/O ports of the simulator, or it could be connected to another simulated component. It needs to be built in a way that it can tell, because it needs to be compiled out of context. Also, as we mentioned earlier in the presentation, we will not compromise simulation performance. This is something that we do well, and we have absolutely no intention of compromising this in any way, shape, or form. Actually, and we've discovered this fairly recently, we will be able to improve performance. The main two reasons we've discovered behind this is by grafting the actual IOs to the simulator post ex facto, we can actually make it so that only the pieces that we're actually using are actually going to have a performance impact. The most simple example of this is calibration. If my scale is going to be 1, then we know that there is no scale to apply, and the system will basically optimize this away. So instead of putting up calibration potential operations in the simulator, we only have the actual active calibration that is happening. On top of this, without getting too much technical, we are integrating bleeding edge software technologies that have been in development within the software industry, most specifically a JIT recompiler. Basically, this means that the simulator is capable of rebuilding itself on the fly to suit its current needs. And this is actually giving us great performance. Finally, we're also improving workflow efficiency. The big thing we're doing here is that we want to minimize compilation operations. So for those of you who have very half models, in some extreme cases, compilations can take up to, how much? Like a few minutes, half an hour easily. for very large models. So we want to minimize this so that you build a model, compile it once, and we're done. The other important thing with the workflow efficiency, and we're going to see this later, is that we're unifying the workflow. By this, we mean that the operation of connecting a model to an I/O, or connecting a model to acquisition, or connecting a model to some GUI elements, it's all the same. There is one way of doing things. Every I/O is being configured using the same mechanism. So by removing the amount of knowledge you need to know to use the various pieces of RT Lab, we're going to make the workflow a lot faster. So to give basically a broad overview of what you just went before, previously, this is what in RT Lab 10 a simulation would look like. I would have a Simulink model. Within the Simulink model, I would have drivers, S functions, various calibration, aliases, data logging, whatever you want. Everything would go in the Simulink model. And then we would compile this and send this to the hardware to simulate. What we're moving to is a model where we have a central core that basically does mapping and calibration. And to that core, we're going to be grafting things from the outside. And then all of those things are going to be connected through connections, calibrated connections, that will allow you to connect a driver directly to a GUI, or connect a GUI to the Simulink simulation, or pretty much any permutations of those things that you may be able to come up with. So there. Now we're going to move on to a live demo that's going to be presented by Philip. That's going to show all of these nice things in action.
Okay, so we just... 2 seconds, I'll get the system ready. Technically, I should have something here. Here we go. So I have a model running right now. Just to show you a little bit the model that we're running. Actually, I have a model running, but the model is totally empty. And what we have done here, so we saw that there is a mapping and connection system in RT Lab. So if we look here, we actually connected a model. So for example, if we look at the Simulink model that is almost empty, let me just move it here. So we got the model. So that's our model. It's actually an empty model. I don't have anything inside this model except a few source. So if you see on the top, I have a duty cycle, which is basically a constant block. I have a 2 sine wave, one sine wave that is a slow sine wave and one sine wave that is a fast sine wave. So really, really, really simple, the most basic model that we can have. Inside this MATLAB model, we can put dynamic models, we can put control model, we can put, EHS, not EHS, but ePhaser sim models, Amiga sim models, sim power system models. So we can put whatever we want inside here. So the purpose of this demonstration is just to show, how we can connect things together. So this is our source model. So right now, what we have done in this system, we just said simply, let's connect the output of the duty cycle to the OPAL-RT board, which is the FPGA. FPGA line. So if we look at the different IOs that we have access on the current simulator that I have right now, I'm looking that I have one board, which is an FPGA, an OPAL-RT FPGA. And inside the FPGA, we have it configured to have 16 analog inputs. We have 16 analog outputs. And we have one function block that is used to do rapid control prototyping for generating PWM outputs. So we have this I/O boards that is accessible from the environment. So the first thing that we did, actually the connection was already made. We took the duty cycle that was coming from the Simulink model. So this is our model here. And we attached the Simulink model to the actual PWM output line of the simulator. So if we want to do a quick test here, I can just delete this connection. And we can try to take the model and take the sine wave, which is the slow sine wave, and connect this one to, again, the same channel that we had, which is the duty cycle 0. So I can take the signal here, drag it to the PWM output, and this is what we get on the scope directly. So I have the model that is running in real time. So the model was already running. And I simply said, okay, now I want to have this output from this model connected to, output number 1 of the simulator here. And this is what we have on the scope right now. I was using a fixed constant, which was generating a 50% duty cycle PWM output. And now I'm just dragging directly from, again, a Simulink model source, which is a real-time model. We connect this to the output of the real-time simulator. So just for fun, we have, I've just put some components here on the system. Let's see what I have on the bench right now. I have a real-time simulator. I have a DC power supply, so this is this guy here, which now I'm outputting almost 11 volts out of it. I have a 6-pulse IGBT coming from LAB11. I have a digital output from the simulator that goes directly into the IGBT of the LAB11 system. Taking the DC power supply, so I'm taking the plus and minus from the power supply, and I'm powering the DC bus of the IGBT, so this is a 6-pulse IGBT. And then we have a filter, we have a load, and then we have current probes. So the current probes and voltage probes, this is this interface here that allows me to measure something, high voltage or high current that is currently flowing into the IGBT. So this one is used to take the measurements. So what I'm taking here, we take one IGBT output, so the bridge here that we have, we go to the current probe, so we measure the current of this line. We go to the filters, and then from the filters, we connect the load, and we go back to the negative part. So I'm just connecting one phase right now, just for the example here. And then we want to know the voltage of the load, so we just take the 2 measurements from the voltage, which are the 1 here, and we connect this to the voltage input of the simulator. So this is to explain the system. So now what we have here, we have a duty cycle going out of the simulator. So this is what I'm measuring. I'm sending to the IGBT. So I'm currently sending this pulse pattern here on the output, so which is a sine wave. So we should be able to generate a sine wave out of the simulator. So now, next thing that we might want to do is to see what's happening for real on the real system. So I know that I'm sending my firing pulses to this guy here. So the first thing that we might want to do is go onto the analog inputs. We can take analog input number 4, which is the DC power supply measurements. So we can drag this out. I have a line here. Actually, I didn't take the time to calibrate, so I don't have the right gain, but that shouldn't be a big issue. So if I put a little bit more power or less power, you see that when we adjust the DC power supply, we can get the feedback here on the GUI. So now, without having any models, I just said I want to have the analog input number 4 from the real-time simulator, so the FPGA that is doing some acquisition, and I just routed this to a scope directly. We're currently using a National Instrument LabVIEW panel here, so it's pretty simple. You don't have to do any LabVIEW code. You just open a VI, you drag and drop some components, and then you can assign directly components from the FPGA to some GUI. So what can we do next? We can say, okay, let's look at the model, because we know that the sine wave that we generate here is coming from the Simulink model that is running in real time. So this is the sine source, the slow sine wave that we have here. And we can say, okay, let's modify the amplitude of this guy. So we drag this to a control. So now we have a 50% 0.5 duty cycle. So if I go to 0, so that since I'm dragging, you see the result directly on the scopes. So now what I've done, I have mapped a parameter inside the Simulink model that is running in real time to a GUI. So when I change the sine gain here, it's actually changing the parameter in real time in the Simulink model. That then the Simulink model is actually sending the output of the sine wave to the I/O boards. And this without changing anything from the Simulink model. So you see, if we go back to the Simulink model, that's the only thing that I have in the system. I just have one source. I map the parameter of this source that is running in real time to a gain. And then the output, I just map it to the IOs. Totally on the fly, no recompilation required. And that's the beauty of this new RT LAB11 environment, is that we can just connect things on the fly like this. And we can do the same thing. I can say, okay, let's now go into the IO. We can go to the carrier blocks and say, okay, let's take the frequency number 0 and drag this to the switching frequency that we have here. So now instead of changing a parameter on the model, I'm actually changing the switching frequency directly inside the FPGA. So I don't even go to the Simulink model. I just map an FPGA parameter that is actually running on the IOs to the UI. So right on the fly. So if we do a quick parallel with the EHS that we saw this morning with Pierre-Yves' demonstration, the IO boards that we have here, it's any FPGA firmware that we have flash on the FPGA. So we can have the EHS board here, so which is our real-time power electronics FPGA firmware that is here. We have all the inputs, so we can, for example, take the EHS, okay, I'm going to send the firing pulses to this EHS, and I will take the simulated measurement out of this EHS, route this to a GUI, or route this to another IOs, or connect this to a Simulink controller models. So everything that Pierre-Yves showed this morning, we can have, the smaller algorithm that we have in the small, is it the Compact Rio, the small one? The MyRIO. So the controller in the MyRIO can be prototyped in MATLAB Simulink. We can have the EHS here that is mapped to an IO board, and we can just prototype the control with a virtual power electronic kernel that is running inside the FPGA. So that's all the purpose of RT LAB11, is to be able to interconnect things together on the fly on the system. So if we extend this now, we have a very simple example of an IGBT where we do real power electronics control. We can map this to smart grid, for example. So that could be something interesting to think of, is that, let's say again, we have our RT LAB11 IO manager. We put inside RT Lab a simulated grid. It can be HyperSim, it can be ePhaser Sim model, it can be Sim Power System models. So these are the real-time grid that is simulated here. And then we connect some UI, so we have front-end user interface that we can connect to it. We can connect RTDMS, ETAP, RT Lab to the IO manager of RT Lab. Then we said, okay, now we want to control the grid. So let's take a Simulink model, compile the model, load the model on the real-time simulator, and attach the controller to the grid so that we can now start prototyping a wide area control. And then what's next? Let's say that we want to connect PMUs or protection devices or relays. We said, okay, let's take some measurements of the simulated grid, take the outputs, go out of the FPGA to analog output, go through amplifiers, and connect this to the voltage and current measurement of PMUs, so that we can actually connect the PMUs, the real one, to a virtual grid, so that we can start prototyping protection scheme or PMU applications. Then what we can do next is take the PMU's outputs, which is typically C37, 118, 16850, and things like that, and we can say, okay, let's feed those measurements out to a simulated telecommunication system. For example, we take OpNet. There are some manufacturers available that we can use, but that's just one example. So we take the measurement, we go this to the simulated telecommunication simulation, and then we connect this one, again, with 61850, C37, to whatever protocols that RT Lab supports. We take the PMU measurement back from a virtual telecommunication system back into RT Lab. So the RT LAB11 is the framework where you can start prototyping things. Higher level wide area control models. You can run grid models. You can run power electronics model on the FPGA. So this is where OPAL-RT is going, with a system that allows you to do co-simulation. And this is really the key point here, is that we can have power electronics running on FPGAs. We can have large power system grid, we can prototype controls, we can connect real devices, we can do control, we can do hardware in the loop, and this is all the purpose of the new RT LAB11 version.
One last thing to point out about the demo that Philip just did is the actual live interconnection that he did not only outside of Simulink, but while the simulation was running, which is no small feat. If the people who worked on this were in the room, I'd thank them right now, but they're not, which is unfortunate. Finally, feature rollout. So we've shown a lot of stuff And RT LAB11 as a product is something that will be evolving over time. We're not planning on shipping all the goodies we described, especially the last slide that Philip showed, immediately as of RT Lab 11.0. So here's sort of where we're planning things out right now. As of RT Lab 11.0, we will be delivering drivers and connections outside of models, live connection authoring, live meaning while the simulation is running, live console authoring with LabVIEW VIs, so the integration of a LabVIEW VI within RT Lab the same way Philip showed today, the connections table that you saw, as well as triggers and data logging. So data logging to files specifically is what we're talking about. On top of that, during the subsequent version of RT Lab 11, we'll be shipping a full-featured alias table, native support for buses within Simulink. So we're talking about putting a Simulink bus and having all the named signals inside of the bus appear directly in RT Lab. Support for non-Simulink models. This is something we just vaguely touched upon. We mentioned ePhaser Sim. Right now, as of RT Lab 10, you need to use ePhaser Sim as a Simulink block. We're planning on removing that criteria away and being able to just say, I want an ePhaser Sim model, this is the netlist I want to use, and that's it, without having to go through Simulink. The same goes for just a simulator made in pure C code, or I'm sure that with time we will have a lot of different things within that category. Importing and exporting the connections table to and from Excel and CSV. This is something that was requested to just have a very nice way of authoring this. A calibration database system, so the connections calibration will probably be coming in RT Lab 11.1, but we'll see. On top of the drivers, we're planning on shipping a full suite of signal builders, signal generators, just various mechanisms to generate signals in real-time performance just outside of the simulator itself, as well as automatic type conversion. By this we mean support for arbitrary data types both within Simulinks and other systems. So instead of just double floating point precision, arbitrary data types will be supported. And that concludes the presentation. Is there any questions? Yes?
In your presentation, you mentioned something about the, I think it was test drive in Orchestra. Could you elaborate a little bit on the Orchestra phase of it?
The Orchestra Framework was kind of the first version of the RT Lab 11. So that was the same thing, but inside Simulink. So we said, let's take the framework of Orchestra. The idea of Orchestra is that you have a Simulink model, you have a block inside that you can subscribe or publish value to it. So for example, you can have a main simulation, and then you have something connected to the main simulation that can publish it and subscribe to this main simulation. It was a little bit static way of doing it, so we needed to, to build a model, to fix everything, to count the number of signals and things like that, so there was nothing really dynamics on this. So we took this concept that was, by the way, required by one of our automotive clients. And this clients that requested this Orchestra Framework first said what, they had some DLL of a simulated car, for example, that they want to attach to a simulation. So they wanted to have this API, the real-time API, to attach third-party libraries, for example, ECU library, wind farm library, or we can think whatever models that we want to attach to a current simulation. So the idea is that we took this concept and we make it standard in RT Lab and dynamic, so that instead of being inside Simulink, we just move all the concept from Orchestra concept to the RT Lab 11 with dynamic connections that allows us to do co-simulation with different tools. So we can have Fortran code, we can have Simulink code, we can have HyperSim code, we can have Dymola, we can have PSIM models, we can have Plex models. So the idea is to really start connecting the different simulation software together, and RT Lab is the main, orchestra that is doing this orchestration of all the signals between all those components. The speed? As Francois was saying, we don't compromise the speed of RT Lab. In fact, we improve on it.
So I can go a little. So the question here was how normally co-simulation frameworks that will add external connections on existing model instead of actually hard coding the connections within them will come as a compromise of speed. So how can we claim that we're going to get better performance out of this? So basically, there's a lot of things that have changed over the past few years as far as software development has happened. And a big thing that has been changing is JIT compilers. And specifically, there's been a lot of development that JIT means just-in-time compiling. So there's been a lot of development on that front, especially funded by Apple over the last few years. And basically, one of the problems one of the reasons behind the actual slowness of the of dynamically made connections comes from incertitude and the fact that you need to have a lot of contingency plans set up for it. With a JIT compiler, you don't have to actually plan for all the contingencies. You can actually build for the specific contingency at hand and deal with that case. We've calculated that the actual overhead for a given connection is 2 nanoseconds. For a given set of connections between a model and between a set of connections between a model and a given I/O. So all the connections between the model and one specific I/O will come at a cost of about 2 nanoseconds. On top of this, though, there's the fact that there's a lot of stuff that can come out of the model. So the model becomes tighter. Calibration does not need to go specifically in it. And this is where sort of the magic happens, is by removing these extra components that are there just in case of you needing them, is counterbalances the fact that there is a slight overhead, but it sort of counterbalances so much that we're coming out ahead in the end.
So it's 2 nanoseconds or 2 microseconds?
2 nanoseconds. We just talk about the connection itself. It's not the overhead to communicate with the IOs, and it's just like, you know, the connection point inside the framework,
okay,
which is really optimized. And just to give an example of what he was mentioning with the JustinTime Compiler, let's say that, you know, you want to connect a Simulink, an IO driver to a Simulink model, and we talk about calibration. So what he means by JustinTime Compiler is that, let's say that you need to add a value, multiply by a gain, and do some kind of signal conversion stuff. You don't need to pre-compile the model. You just said, I want to add a gain, +5, and do some mathematical equation. The just-in-time compiler will take this new equation, generate the binary code, load this into the simulator, and now we're going to have this little piece of code that will do the math that is required to do the calibration. So this is what is the just-in-time compiler. Instead of having to go through the whole cycle of recompiling the whole model just because we change the calibration, we just take the equation, generate the code, and plug in the code into the real-time environment. So that's what is the just-in-time compiler stuff.
Is when you're talking about the adding code and just in time, but if you have a simulation running all the time, is this creating kind of latency or time to improve, or so do you have a stop in your simulation during a certain amount of time?
No. So the question is, because we're going to be doing dynamic compilation of the actual code for the connections, while that compilation happens, are there any delays that happen? And the answer to this is no. Basically, our targets, like the OP-5600, this is a 12-core target, I think, specifically here. And what we actually have is that we reserve 1 core for basically the management of the simulation. So that core normally is being used for communication with the host and other things. So what we actually do is that we compile the actual requested connection on basically the communication core, and once the connection is ready, then we insert it into the real-time simulation. It's a little more involved than that. It gets a little technical. I don't really want to get into too many details, but there is essentially we sort of really between two time steps, we have a very tiny operation of switching two pointers. So it is practically not mentionable. Yes. So the question was when you're dealing with IOs or if you're dealing with various types of connections, this goes back to the idea that of contextual independence. The system doesn't know what is connecting to what. It knows how to make connections between two things. And the thing being an IO, driver, or an actual model, it's irrelevant as far as the system is concerned.
And this is what we have done with HyperSim recently. All the I/O modules that we connect to the HyperSim cluster is all going through this I/O mapper. So eventually we can think of connecting HyperSim to RT Lab or HyperSim to other software with this. No. It's HyperSim. We can publish some measurements to the I/O manager, and then we can make the connection to whatever PMU or other devices in real time. So HyperSim is talking to the simulation engine here the same way as is connected to the IOs.
So there's a bit of a detail here. I want to make sure we're clear. HyperSim uses this underlying. However, HyperSim is not currently connected to the GUI. So while HyperSim is technically capable of adding the connections on the fly, as of today, it's still all being applied during load. This is something we're hoping we can integrate in the future, but there is no. As of today, the actual live modification of the connections is there, but not accessible.
The question, yeah?
Yes, thank you. This is very exciting, I think. I cannot wait until starting to use it.
So this is going to be
big news. I don't know if people are aware of what is this.
Well, this will simplify a lot the use of RT Lab. You just have your Simulink model. You don't do any modification to it. You just load in RT Lab. And you start connecting IOs on the fly.
Yeah, I remember, I mean, we are starting, or we started to implement this now, but I remember this vision we had, Jean had for so many years.
A decade.
Yeah,
more than that.
Exactly. So to see it happening is really very exciting. I have one or two questions that are related to each other. First, about the distributed computation. I guess this will still be, this is the core of our RT Lab features, is about distributing a model over several processors, several cores. So this will still be...
to split on multiple core when using MATLAB Simulink, it's going to be the same way as we used to do. One of the challenge with MATLAB Simulink is that since it's a multi-model simulation, we can have electrical components, we can have mechanical components, we can have all kind of different type of models. There's no magical way of splitting those models. Then as regards of HyperSim, for example, which we know the type of models that we have, HyperSim is able to split the power system model automatically. So because Simulink is providing us this level of flexibility of mixing everything together, control, power electronics, power system, mechanical simulation, there's no magical way of splitting the models right now. But when we talk about EHS or HyperSim, then since we know the math behind, there's a way that we can split it automatically. So okay. I would say we are half there. For power system, this is done. For like co-simulation with mixed domain simulation, that's something that we don't have yet.
Another question, do you see that by having this new paradigm in RT Lab, there will be an improvement of supporting the IP in models between teams, for example, or between customer and supplier? For example, if I have a model that I want to give to my to a client, for example, I can protect it because
it's all inside. Well, right now you can take it of a code, and what we plug in. For example, we do talk about Simulink, we talk about ePhaser Sim, we can talk about a binary code. So if you have a supplier, that's exactly the purpose of this environment, is sometime, for example, if we think at one of our aerospace customer, Embraer, they receive from their suppliers binary codes of the different components of the airplanes. For example, the nav communication computer, the engine dynamics. So this is for aerospace. If we think about, for example, power system, we can receive from G, for example, the model of a wind turbine, but they don't want to share this model. So you receive this as a binary code, and you just bring the binary code and plug in this to RT Lab. The only thing that we need to supply to those guys is that, okay, just put this hook into your code so that you can tap into our real-time API and connect the thing together.
So there is an improvement. I mean, a better support now in protecting the
That's correct, exactly.
IP.
Other questions?
Sean, you want to do a final note?
Final comment from John? Yeah, take this one.
So I have to say that I'm quite excited. I would like to go back 30 years ago. It's like the dream is to bring now the video games to the engineering. Okay, making engineering has to be fun. Okay. This is why that now François is coming from the game industry, so we try to bring the software to this age, so we can attract young engineers. Okay. So I'm quite excited. So thank you guys.